Hi, welcome to the first video we're going to do about chemistry and the process of teaching it remotely, not face-to-face. What I want to talk about with this first short video is some representations of molecules. So there's a handout for this on Blackboard. I'm going to be using the handout. If you can print it, fine. If you want to make notes on it, fine. Whatever, but that's going to be the standard format for these. So in addition to showing you some stuff, I want this to be sort of our intro and how we're going to use these videos. So we can draw molecules a lot of different ways. We've already seen that. We can represent molecules with Lewis structures, but remember the important thing about the Lewis structure is it doesn't give a representation of the three-dimensional shape. We can use the Lewis structure to figure out the three-dimensional shape, and that's what we do with VSEPR. And so once we know the three-dimensional shape, we can use VSEPR and its results to try to visualize the molecule in a little bit more accurate manner. Okay, so for example, if I draw the Lewis structure for methane, CH4, I'm going to draw something that looks like this. Now, if I wanted to show this thing has an electronic geometry of tetrahedral, since there's 4 regions, it has all bonding regions, so it has a molecular geometry of tetrahedral. This is how we can represent a tetrahedral subspecies with dashes and wedges. The wedges mean the H is coming out. The dashes mean it's going back. The H's and the carbon are all in the paper. So you can imagine this H was sticking out of the paper or the screen. This H was sticking behind the screen. Another way that you'll see this represented is with ball and stick drawings. This is trying to emulate if you were to build a model of these things. Okay? And if we were in class, we would be building models. When you take organic, you'll do a lot with models. So here's a model, a ball and stick drawing of methane. Now, if you use the PhET app like I showed you in class and like on that other assignment, it shows these and you can wiggle them and draw them around and spin them around and do all sorts of things with it. If I look at a molecule with lone pairs on it, like ammonia, here's how I might draw a Lewis structure. Again, it doesn't matter really where you put the bonds of the lone pairs. It's just there's a nitrogen with four regions, 3 of them bonding, 1 of them lone pairs. The electronic geometry here is tetrahedral. The molecular geometry for this species, if you remember, and you should because I'll ask you, is trigonal pyramidal. So this looks like a trigonal pyramid. Again, notice this looks a lot like our tetrahedral molecule above. We've got the nitrogen, the lone pairs, and the H in the plane, and we've got an H coming out and an H going back. That's another way to draw this. These dashes and wedge drawings are going to be all over the place in organic. You'll see them in the book. You'll see them online. Just wanted you to get some experience with them. Now notice this ball and stick drawing. Where the lone pairs go. Remember, the lone pairs are really right here. But when we look at a molecular geometry, we ignore the lone pairs, right? So a ball and stick drawing is actually showing you the best view of the molecular geometry. Those lone pairs are there, but we don't see them. But we know they're there. So the presence of the lone pairs causes this not to be flat. It causes it to be trigonal pyramidal. So that if I see this shape, I have to train myself to realize, oh, there's a lone pair there. Because that shape corresponds to 3 bonds and 1 lone pair. It's just not shown. If we look at water, we see the next step up. We've got 2 lone pairs on the oxygen. Here's our Lewis structure we might draw. We could draw water a couple of different ways. We can draw it with like this. An alternative way to draw it, which I can use with the dashes and wedges, is I might have the H's coming in and out and the lone pairs in the plane of the board. Either way, it's just an attempt to show that this electronic geometry here is tetrahedral still, 1, 2, 3, 4. And I've got H's coming in and out, or all 3 of these are lying in the plane, and the electrons are going behind or in front. Again, if I look at the ball and stick model, notice I don't see the electrons, but I see the effect of them there. They're inferred. So a couple things to sum this up. What the dashes mean is an important thing for you to keep in mind. And in the ball and stick drawings, the lone pairs aren't seen, but we can tell they're there because of the shapes. If there were no lone pairs on this central atom, this would be linear. But because it's not linear, there must be something there. All right. We can do this with more complicated molecules, and this is what we'll start to see a little more of. So for example, here's an amino acid. I think it's glycine. It conveniently tells me that. And so I'm not going to ever talk about a shape of this molecule, but what I can talk about is a geometry around each of these atoms. I can say this is the central atom with 1, 2, 3, 4 things. Here's a central atom with 1, 2, 3, 4 things. Here's a central atom with 1, 2, 3 regions. Here's a central atom with 1, 2, 3, 4 regions. So I can talk about the geometry here, the geometry here, the geometry here, and the geometry here. And that's what this picture does. I borrowed this, don't tell on me. And so here's a ball and stick representation of it. And you can see it's trying to show that this H is behind and this H is out in front. This H is sort of coming toward you. This H is going that way. But because this isn't flat and planar, we know that there's a lone pair there. Okay? Because it's a nitrogen with 3 bonds in a lone pair. The lone pair is just not shown. It's as if we were looking at a model. If I look at this oxygen up here on the carbon-oxygen double bond, there's 2 lone pairs here. They're not shown. And if I think about this oxygen, it has 2 lone pairs, one there and one there, but they're not shown, but their effect is there because this looks bent. Okay? Just got to get used to visualizing and seeing these things. The last thing that you'll see some of, and we'll see some of these later when the molecules start to get bigger, is these things called space fillings. They're very much like ball and stick models. The difference is it's trying to show that that is the size of the hydrogen's electron cloud, that's the carbon, that's the hydrogen. So these are really trying to show the relative sizes of the atoms involved. Because one thing that you might expect in this model of glycine, there's really not all this empty space right here. Okay, this takes up more space than this. This is just sort of showing you connectivity. It's much more compact and there's more stuff, there's more electron density there. This is trying to show you all of that.